Thank you very much. And of course, let me join the other speakers in thanking the organizers for putting together such a nice workshop with so many interesting discussion sessions and talks and so on. And thank you as well for giving me this very nice nap slot to present my work. I will do a very non-Spanish thing to do, which is to ask you not to take a nap and stay with me for the next 30 minutes. And yeah, let me position myself strategically close to the... Okay, so yeah, today we'll be talking about this work in collaboration with Dieter and Marco here in the audience, maybe. And also with Joaquin Macias, who's a very good PhD student at the Max Planck Institute as well. And before even starting to tell you about the species thermodynamics and black hole tower correspondence, let me try to warm everybody up a little bit, well, not too much, but just setting the stage and reviewing some things that probably we've all heard about. But okay, this is working. Now is to just move this. Okay. And okay, so the species scale, I mean, let's say the way to motivate it is to think about it as the maximum UV cutoff in quantum gravity. And in particular, this is the way it was motivated in the original work by Dwally and then formalized in these other works, also with Dieter and Cesar and other people. And basically what it captures is the idea that an effective theory of quantum gravity can break at scales well below the Planck scale. In particular, if the number of light species is large enough. So I will not go into the details of defining the species scale. This could be enough for a discussion. And in fact, we will have a discussion right after the talk about the species scale. So let me just comment on a couple of key things for the rest of the talk. The first one is that, as I was saying, this can be very important in the presence of light towers of states, which is what we're used to in the Swampland program. And in particular, in this talk, I will focus about the limits of moduli space, so when this number of species is large. And therefore, I will consider, in general, towers of states with levels given by this. I will use this parameterization just for concreteness during the talk. In the paper, we do much more general cases and so on, but just for concreteness, let me stick to this, where basically this P here, I mean, this MT is a scale, typical mass scale of the tower. You can think of it as the KK scale, the string scale, if the tower is given by string oscillators. And this P is effectively parameterizing the number of dimensions that they compactify. If it's a finite P, you can write basically everything like the lambda species and the number of species in terms of these parameters. And also let me mention that this P, in the limit in which it goes to infinity, is capturing a stringy tower. So as I said before, for some things one has to be more careful, but for now, let me just stick to this. And basically, the number of species in these cases is given by 1 over the string coupling squared. Now, the key message that I want to just recall for everyone is that depending on what kind of infinite distance limit we're probing, and of course, taking into account the emergent string conjecture, I will comment a bit more on this later. But basically, we have a decompactification of p dimensions. The species scale is capturing roughly the higher dimensional Planck mass. I should probably say, to be more precise, that it's capturing the higher dimensional species scale, but then it wouldn't be very helpful for the people who don't know what the species scale is. So let me just say that parametrically it captures higher dimensional Planck scale or the string scale, modulo some subtleties. But the definition of the species scale that I want to focus on in this talk is the definition from the radius of the smallest black hole in the EFT. Because basically it's a sensible thing to do to consider as the cutoff of my gravitational theory, the inverse of the length scale associated to the smallest black hole that I can describe in it. And in particular, this was also in the original work, and this has been used to also motivate these behaviors here. And I want to emphasize that in this case, this smaller black hole, if one just naively introduces the definition of the species scale here, has an entropy which is given by the number of species. So this motivation, this idea from the black hole perspective is actually going to be one of the main things I'm going to be exploring in this talk in the context of trying to derive this kind of behavior for the entropy from standard thermodynamics of a species in a box. The next thing that I want to recall for everyone is that the fact that precisely when we're considering configurations of, in this case, a species at thermal equilibrium in a box of size L at energy E in the presence of gravity. If I want the EFT to still be a good description, one thing that I probably need to ensure is that the configuration doesn't collapse into a black hole. And this is ensured by the fact that the typical length scale of my box is bigger than the Schwarzschild radius associated to the energy of the box. And then another interesting bound that we have, or another interesting property that we have in gravitational systems, is the covariant entropy bound that we know basically is telling us, in this case, that the entropy, the maximum entropy that I can accommodate in such a box, is basically given by the area and Planck units, or equivalently, but by the entropy of the black hole of the same size as the box. And in general, like if you assume some relation between the energy and the temperature, which goes like this, which is in fact what will be the case in all the cases we consider, as I will show, you can think of this, of course, as some upper bound for this typical, for the energy in terms of the length of your system or for the entropy. Now, the thing here is that if you look at these two bounds, for example, you see that you always, for temperatures, or for configurations in equilibrium at temperatures above 1 over L, which are the ones that you want to consider for the particles inside the box, one always reaches this energy before reaching this one. Namely, if I consider a box at temperature T and length, typical length scale L, and I start heating it up, what will happen is that simply at some point, when the entropy hasn't really got any close to saturating the covariant entropy bound, I can saturate the gravitational collapse bound, the thing collapses, and it automatically has the maximum entropy, but because it became a black hole. But there is some kind of discontinuity in the entropy, and therefore we cannot really learn much about the entropy of these black holes from the entropy of the system we started from. So the question here, in order to try to get some insight about the entropy of these configurations, these minimal black holes, or the entropy that we can associate to species, is first, can we approach the maximum entropy? Maximum entropy understood as, can we approach saturation of the covariant entropy bound for these configurations for some non-black hole configuration? And then the second question is, as I was telling you, since one should, as we will make clear in a second, like since this is related to the smallest possible black hole, can we understand this as a limiting behavior from a black hole? So can we have some kind of smooth-ish transition? And these two questions are the ones that I'm going to try to address in the rest of the talk, and they bring me to the title of the talk again, because the first one is precisely the first part of the talk, and the second one is the second part of the talk. Yes? Yes? Mm-hmm. No, so I mean, what you mean for the CKN bound, basically where they get the maximum, I mean, the CKN bound, basically what they do is in fact to consider these kind of configurations and declare that they don't want the thing to collapse gravitationally, but they are taking into account particle states. And what we're gonna do here is to consider the contributions from to the entropy only from the tower of weakly coupled particles. But then we will see that this, in some limit, corresponds to the one of the minimal black hole, but in a way that I will make more precise. If I'm not answering your question in a while, just go again, please. So a first hint of trying to approach this configuration from without collapsing the thing into a black hole, or let's say marginally collapsing, is the fact that these two bounds coincide when t equals 1 over L. Basically because effectively one is freezing the momentum degrees of freedom. And what happens is that in this case, the two are the same, and therefore one can think of trying to play with the different control parameters of the box, namely not only the temperature, but the length, and trying to play with them in a way that I can heat the thing up without it collapsing into a black hole too soon. So after presenting the general questions that we want to address in the talk, let me try to go, as I said, to the two parts. First, the first thing I will try to do is indeed just a very simple thermodynamical argument for accounting for this species entropy from the entropy of a tower of particles as it approaches the limit in which it collapses gravitationally. So as I said, just consider a configuration of particles in a box of size L in the presence of some light species, and then we will do it keeping in mind that we want to be close to the weak coupling regime, namely close to the large infinite distance points in moduli space, or that there's enough of these guys, basically, so that we can neglect other contributions, and the leading contributions are always given by the large number of species. And then, first thing one can do is we're taking the free approximation, because indeed the d-dimensional Planck mass is much greater than the species scale, which is the maximum scale for this tower, and we avoid gravitational collapse. And the first thing one can do is just use the following partition function, which is just partition function for a system of free particles. It's just the product of one particle partition function. So I consider the one particle partition function for n species, where n gives the label of the species. Basically, if I have n sub n number of species, like one particle states of a species n, I just multiply n times, and then I correct, of course, for quantum indistinguishability of particles. So I correct by the n over n sub n factorial. And then I do this for all the species that are active at temperature T, which I label NT. And these two things, like NN and NT, I'm not fixing them or anything, just leaving the thermodynamics tell me what they are. So as I was saying before, like if I consider a box in which the temperature is much greater than the length, what happens is that I have a lot of phase space available as related to momentum states per particle, and one has this typical scaling with the volume of the box. These, as I said, are fixed by the thermodynamics. So basically, as one could expect, I mean, I'm just doing basic thermodynamics here, as one could expect for particles with masses below the temperature. Basically, I have no suppression. So this, the number of available phases, momentum states for each of the species is populated. And then for the ones with masses above, I have the typical Boltzmann suppression. So basically, they don't contribute significantly to the partition function. And then the number of active species, precisely because it's effectively cut off at masses equal to the temperature, is just given by the number of particles that are below temperature T. So with this, again, basic thermodynamics, I get this expression for the energy, this expression for the entropy, and I get the usual volume scaling of the entropy, like T times LD minus 1. And this is like the first thing, like you do this, and then, as I said before, like one could be worried, okay, how can this fulfill the covariant entropy bound? In fact, it doesn't happen because the thing, before it reaches it, it should collapse. But what if I try to, again, maximize this, keeping the configuration without collapsing into a black hole? What happens is that, as I said, let me just make a very small box, given by 1 over T, and then I simply get that the entropy scales like the number of active species, temperature T. And this is already at the core of this so-called species thermodynamics, because species thermodynamics is simply telling you that you can associate an entropy to the species that is equivalent to the one of the minimal black hole, and an energy which is equivalent to the one of the minimal black hole. And here we have something that very much looks like it, except for the fact that this T is not lambda species, and therefore this N is not N species. But now with these formulas, I can simply go and see how much I can raise the temperature until I reach the covariant entropy bound and the gravitational collapse bound. And indeed, what I find is that the maximum temperature, where this is saturated, is given by lambda species, which is roughly what we get in the common room at lunchtime. But basically, this is the only, I mean, the main idea in this work is that from basic thermodynamics, we can recover this in the right limit. And basically, the main message is, in the limit in which I have low temperatures and momentum states dominate the entropy, I get the usual volume scaling. In the limit in which I make the box small and effectively freeze the momentum modes, I get the scaling of with lambda species. And this is basically has the same scaling of the energy and temperature as a black hole. And then I have some intermediate regime in which I can interpolate between the two. So this is like basically these constitutive relations for species thermodynamics that were somehow observed. What we're doing here is just not assuming anything about the, like we're not imposing them, we're not assuming them, we're just deriving them from basic thermodynamics. Now, with this idea that basically the box is similar to a black hole, one can try to push this a little bit further and go to this black hole tower correspondence. Because what we're doing is like, if you take a large black hole and you make it as small as you can, well, we said before that the smallest black hole you can get is order lambda species to the -1. I will go into that in a bit more detail. But basically, you can approach this limit in which you get the smallest possible black hole. You can go from the EFT side and reach the maximum possible temperature. So both of these limits go to the maximum possible temperature, and you get something that basically has the right entropy and energy. And therefore, one can try to think if this is a general way of understanding this correspondence near this point where I have boxes or objects of size lambda species to the -1. So to do this, what I want to do is to briefly review the black hole string correspondence as originally proposed in the 90s, and then also revisited recently, also in the context of the Swampland and so on. And to do that, what I will do is review the original motivation or argument given in this paper by Zaskan in 93. So I want to make a disclaimer here. I'm not going to be talking about the dynamics of the transition. I'm going to be talking about the kinematics, namely about this correspondence between entropies and energies between the minimal black hole and a system of species at thermal equilibrium. So to understand this in the concept of the original black hole string correspondence, let me just consider a theory, a string theory, where the Planck length and the string length are, as usual, related by the string coupling. Let me stay at a fixed point in the string coupling space, call it G0, and let me consider a very big black hole. I consider a very big black hole. Its mass and entropy are given by the usual formula here, and I'm just rewriting them here in terms of the string length to plot it here in string units because it's just more transparent. It's not, there's nothing special about string units. It's just more transparent here. And then what I want to do, which is just what was proposed in this original argument, is let me make the string coupling very small. Let me move towards small string coupling while keeping the entropy of this object constant. What happens if I do that is that the mass of the object increases in string units. Its length decreases. And therefore, the original motivation for this was, okay, maybe I reach a point where, because I'm making GS arbitrarily small, I'm making gravity arbitrarily small, maybe there's a point where actually gravity cannot keep the black hole a black hole, and the thing transitions to something else, because gravity is too weak. And the proposal was that, in fact, at this point, what should happen is that the black hole somehow transitions to a very long string or a system of strings, but the thermodynamics of this guy is dominated by a long string. But for this to actually happen, it should have the right entropy and energy. And in fact, what happens is that if you consider a free string, so because we are at very small string coupling, which has this form of the mass and this form of the entropy, indeed, and if you follow it now from the right to the left, indeed, it meets the black hole curve at this particular point, which is precisely when the radius of the black hole is of the order of the string length, and the mass is also given by the mass of the black hole of the minimum given by string length. And in fact, its entropy is given by 1 over the string coupling squared at the correspondence point, which is nothing but, if you remember from one of the first slides, the number of species that you can define for a string scale. This can actually be used to define the number of species in the string case. And now the statement is, I take this very large black hole, I follow it to weak coupling along constant entropy lines, and in fact, I can account for its entropy, because the entropy is constant along all these trajectories, I can account for its entropy in the free theory, in the GS going to 0 limit, just by the entropy of the counting of the string ensemble. In fact, this happens not only for this point, but along this line, if I take different black holes, and the statement is that this should happen for, let's say I am at G0, I start considering lots of big black holes with masses here, 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 as large as you want, and then you follow them, all of them will cross this line at the point at which the radius of the black hole is given by the string scale at the corresponding point, and all of them, all their entropies can be written as the number of species at the corresponding point. You have your black hole region, your free string region. And therefore, what we are doing here, because we showed that indeed, if you consider the system, the thermodynamic system of particles in here, in thermal equilibrium, the free system, and you approach this point, it always, like what I showed you before, is that in fact, it always has the right string the right entropy and the right mass to map to meet the one of the minimal black hole, one can just generalize this to a black hole tower correspondence, also in the case of KK states, not only of string states. And basically the identification is pretty simple. It's just what was the correspondence point before, which was the string length, now is L species, which for string towers is the string length, for KK towers is the higher dimensional, parametrically the higher dimensional Planck length or string length. Then one can just, the scalar that you follow towards weak coupling is just the one basically giving, measuring for you the relative intensity between the effective Planck mass and the species scale. So if you now probe at the compactification limit, and again, take a very large black hole, and then go towards large volume, this thing will become smaller and smaller, and along constant entropy lines, this thing will become smaller and smaller, and then eventually you reach this point where it has species length along the non-compact dimensions, and then it has the right entropy energy to meet the system of particles in the tower. There's some subtlety here when you reach the energy of when you reach sizes that are of the order of the internal dimension. I don't have much time to comment about it, but I would be happy to discuss it. But basically, it doesn't change the argument because, as I said, we are following this line of constant entropy, and we are not really focusing on the dynamics, but on the kinematics in the sense of this guy existing, this black hole existing in the spectrum of my theory. So this is the general rule, and I showed that it works for, well, I didn't show that it works for string towers. Many people showed it long ago. Here we see that it also works for KK towers. And then one could ask, like, what about other towers? And precisely what one can argue is that only the towers that are allowed by the emergent string conjecture, namely KK-like towers or string-like towers, have the right limits in the entropy and energy to actually account for the entropy and energy of the black hole. Namely, you have a very big black hole, and you want to map it in the free limit to a system that can account for its entropy. You can only do it with KK towers, namely polynomial density or exponential density of states, like the string. This was also, like, there's been a nice works in the last 7-8 months, precisely giving bottom-up argument for the emergent string conjecture. This one's precisely assuming or using the laws of species thermodynamics that I was trying to motivate here from that we actually obtained here from this simple thermodynamic ensemble. This one here by Max and collaborators, also from the structure of amplitudes. And what we see is that indeed these two are okay, but super exponential and sub-polynomial, namely less density of states and larger density of states, do not give the right scalings. Yes, Nacho. Yes. Mm-hmm. Mm-hmm. Let's say in general, actually, the only thing you actually care about in this sense, actually, you remember before I was writing is like 1 over P, is actually that the scaling indeed of the number of states as you approach the species scale doesn't grow too fast. So I think asymptotically, anything that you can like basically approximate by some effective polynomial scaling, if it goes, so you say it's something like n mt and the density goes log n? Log n here. Log n here, and then here this is polynomial? We can discuss about that later. But I think in general, we didn't check for, let's say, I mean, basically you have log here, but then you have some polynomial thing here. Yeah, that's log n, and, but log n and polynomial? But log n and polynomial, like the ones generalized here, yeah, but this should actually be equivalent to exponential towers, right? Because it's like you can relabel log n and then here. Yeah. Yeah, but I think you can effectively parameterize it as an exponential tower. Just relabel log n, like n prime, and then this n here as E2. Yeah. Okay, so let me just summarize what I did, and we can all go for, well, for a lot of questions, of course, and then coffee. So in the first part, I just tried to basically derive the constitutive relations of species thermodynamics, which are basically the entropy and the energy of these minimal black holes from basic thermodynamics of the species. And basically, we did this in a way that, of course, doesn't collapse gravitationally and approaches the maximum possible entropy, understood as asymptotically saturating the covariant entropy bound. And we recovered, as I said before, like the usual volume scaling in the right QFT limit, let's say when the temperature is much greater than than 1 over L, and basically not a lot of species enter the game. And in the limit in which basically we get a lot of species dominating, we get that for T approaching the maximum temperature, which is given by lambda species, we get the right entropy and energy, of course, I'm not showing it here. And then in the second part, I told you how these towers can give rise to a tower black hole correspondence in the sense of really having this meeting point, let's say, along for every value of the field that you're taking to infinite distance that is basically controlling for you the gravitational coupling such that at each point the entropy of a black hole can be mapped to the entropy of a system of 3 species. And then basically that in the limit as T goes to lambda species, only this or like basically super exponential or sub-polynomial kinds of towers cannot give rise to the right constitutive relations. So I would like to just end with some open questions or food for thought, because basically we are here like in this workshop with lots of discussions. So let me just throw this here. This is speculative. I really don't have much to say about this, but if anyone is interested in discussing any of these things, I would be happy to do so. So thank you very much, and that's it.